Welcome to Math Science History, the podcast that explores the overlooked brilliance, the unexpected intersections, and the incredible individuals who have shaped the scientific world one story at a time. I'm Gabrielle Burchak, and by the time you're done listening to today's podcast, you're going to know a lot more about the woman who literally redrew the boundaries of Earth, and still for decades her name was left off the map. This is the story of Marie Tharp, the geologist and cartographer who helped prove the theory of continental drift and changed geology forever, armed with nothing more than sonar readings, colored pencils, and a determination to reveal the unseen. Marie Tharp was born on July 30th, 1920 in Ypsilanti, Michigan. Her father, William Tharp, was a soil surveyor with the U.S. Department of Agriculture. From a young age, Marie traveled with him across the country, watching as he documented the land. This early exposure to map making laid the foundation for her future, though neither she nor her father could have predicted she would one day chart landscapes no human eye had ever seen. She earned degrees in music and English from Ohio University, but her path wasn't fixed. Her early interest in science, inspired by her father's soil survey work, lingered in the background. During World War II, as men were drafted and college enrollment numbers dropped, universities across the United States opened their classrooms to women in an unprecedented way. For many, it was the first, and for some, the only invitation into male-dominated scientific fields. So Marie seized that opportunity. In 1943, she enrolled in a wartime accelerated petroleum geology program at the University of Michigan. Oil was essential to the war effort, and the petroleum industry suddenly needed geologists fast. The program was intensive, practical, and groundbreaking. For Marie, it was also the first time she was surrounded by women who were serious about science. She earned her master's degree in geology in 1944. After graduating, Tharp worked briefly for Staniland Oil in Tulsa, Oklahoma, analyzing well logs. But the field work was mostly off limits to women, and the work felt limited. Tharp wanted more than oil wells. She wanted to understand the planet. Driven by this deeper intellectual curiosity, she returned to academia, this time pursuing a second degree in mathematics at the University of Tulsa. It was this added credential that eventually opened a door for her at Columbia University. In 1948, Tharp was hired as a research assistant at Columbia's newly formed Lamont Geological Observatory, located in Palisades, New York. Lamont was at the forefront of oceanographic research. Funded by the Office of Naval Research and driven by Cold War curiosity about what lay beneath the oceans, the lab was gathering a flood of sonar data from expeditions crisscrossing across the Atlantic. This is where she met Bruce Heezen. He was a dynamic and ambitious seismologist, 6 years her junior. Heezen had a reputation for being bold and occasionally brash, but he recognized that Tharp had skills that no one else at Lamont did. She could read seismic and bathyrismic data like a second language, and, more importantly, she could visualize it. Heezen had access to the data, and Tharp knew how to turn it into a map. So their partnership formed, not out of social camaraderie, but mutual utility. Heezen needed someone to process the stacks of echo soundings from his expeditions, and Tharp needed a way to stay connected to field science without being allowed on the ships. Together, they began mapping the ocean floor one echo at a time. You see, in the early 1950s, oceanographic data was gathered by ships using echo sounding, a sonar method that involved bouncing waves off the seafloor and recording the time it took for the echo to return. Men like Heezen were allowed to go on the expeditions, but women, like Tharp, weren't allowed. So instead, Marie Tharp remained on land, poring over endless columns of sonar data, meticulously converting numbers into depth profiles and maps. She noticed something strange. a continuous V-shaped valley running down the center of the mid-Atlantic ridge. It looked like a rift valley, similar to those on land, like the East African Rift. If true, this V-shaped valley could support Alfred Wegener's long-dismissed theory of continental drift. You see, Alfred Wegener's theory of continental drift, which was proposed in 1912, suggested that the continents were once joined together in a single massive landmass. He named this Pangaea, and he proposed that it had since drifted apart over millions of years to form the continents that we see today. The key elements of Wegener's theory included the idea of Pangaea, wherein all the continents were once connected in a supercontinent. This supercontinent, he proposed, began breaking apart around 200 million years ago. Wegener proposed that continents moved across the Earth's surface over geological time, eventually drifting through the ocean crust like icebergs floating through water. The evidence that he cited included the fitting of the continents wherein the coastlines of the continents, like South America and Africa, appear to fit together, like puzzle pieces. He also noted that identical fossils of extinct plants and animals had been found on continents that were now separated by vast oceans. Additionally, he proposed that similar rock layers and mountain ranges, like the Appalachian Mountains in North America and the Caledonian Mountains in Scotland, are found on continents that are now far apart. Finally, he provided paleoclimate evidence showing that glacial deposits now shown in tropical areas indicate that the regions could have once been much closer to the poles. Unfortunately, Wegener's theory was widely rejected by the science community, and there are several reasons why. Wegener couldn't explain how the continents moved. He suggested they plowed through the ocean floor due to gravitational forces or centrifugal effects from the Earth's rotation. But his ideas weren't physically plausible. He did not have a convincing mechanism, and as a result, his theory lacked scientific rigor. His theory also conflicted with other theories at that time. In the early 20th century, many geologists believed in fixism, which is the idea that continents and oceans had always remained in the same place. Additionally, interdisciplinary thinking wasn't embraced at this time, and sadly, it still isn't embraced. Wegener was a meteorologist and an astronomer, not a geologist. Many geologists were suspicious of an outsider proposing a radical theory in their field. Finally, Wegener was German. As a result, post-World War I political tensions made some scientists in Allied nations less inclined to accept his work. So, many years later, when Tharp showed her findings to Heezen, he allegedly dismissed them as girl talk and then made her redo the drawings. Undeterred, she kept mapping. Good for her. The data kept showing the rift. Eventually, Heezen accepted her conclusion, and together they published what would become one of the most important maps in modern geology. It was a profile of the North Atlantic ocean floor, revealing the central rift valley of the mid-Atlantic ridge. This was more than just a topographic feature. It was a smoking gun for plate tectonics. So, why are plate tectonics important? Well, plate tectonics explain the movement of the Earth's crust. The Earth's outer shell, its lithosphere, is broken into large slabs called tectonic plates. These plates float atop the semi-fluid layer of the mantle and move slowly, about as fast as your fingernails grow. Where these plates interact, we see geological action. Mountains rise, oceans open, and continents drift. Second, plate tectonics are important because they help us understand earthquakes and volcanoes. Most earthquakes and volcanic eruptions occur along plate boundaries. So, where plates collide, these are called convergent boundaries, one can sink beneath another, creating volcanoes and earthquakes. Also, where plates pull apart, these are called divergent boundaries, magma rises to fill the gap, forming mid-ocean ridges like the one Marie Tharp discovered. And then also, where plates slide past each other, these are called transform boundaries. They build up stress that releases as earthquakes, like along the San Andreas Fault. The third reason why plate tectonics are important is that it reveals a deep history of the Earth's continents and oceans. Plate tectonics explains how Pangaea, a supercontinent, broke apart about 200 million years ago, leading to today's arrangement of continents. It also helps geologists reconstruct past climates, trace the evolution of species, and predict future continental movement. The fourth reason why plate tectonics are important is that it drives Earth's rock cycle and surface renewal. Without plate tectonics, Earth's surface would be geologically dead. The recycling of ocean crust and uplift of continental crust drives mountain formation, earthquakes, volcanoes, and the carbon cycle, which regulates the Earth's climate. The fifth reason why plate tectonics are important is that it's crucial for locating natural resources. Oil, natural gas, minerals, and geothermal energy often occur near tectonic boundaries. Understanding plate tectonics helps scientists locate and manage these resources safely. And finally, the sixth reason why plate tectonics are so important is that it helps unify geology as a science. So before plate tectonics were accepted in the 1960s and the 1970s, geology was a fragmented field. The theory of plate tectonics gave Earth scientists a unifying framework that tied together previously disconnected observations from fossil distribution to mountain building to seafloor spreading. So, in other words, Tharp was unifying all these different fields in geology. And as a result, between 1957 and 1977, Tharp and Heezen collaborated on a series of revolutionary maps of the seafloor. We'll be right back after a quick word from my advertisers. Their work culminated in the 1977 publication of The World Ocean Floor, a colored map created in collaboration with Austrian artist Heinrich Baron and the U.S. Navy. This map and Tharp's discovery visually confirmed what many scientists had resisted for decades, that the Earth's crust was in motion, splitting apart along vast underwater mountain chains. As a result, Baron's artistry, Tharp's mapping, and Heezen's data collection combined to show a textured, dynamic Earth previously imagined only in theory. Trenches, ridges, rifts, fracture zones, they were all there. But for all this groundbreaking work, Marie Tharp's name was initially left off the credits. Heezen was listed as the primary author on most papers and maps. Tharp, as a woman in a male-dominated field, was kept in the shadows. She couldn't join research expeditions, she didn't get tenure, but the maps bore her mark through her fine lines, her careful interpretations, and her legacy. Marie Tharp's name was never formally printed on the original 1977 World Ocean Floor map, despite the fact that it was largely based on her data interpretations, hand-drawn physiographic profiles, and decades of her work. However, her name began to be publicly associated with the map in the 1990s when institutions like the Library of Congress, National Geographic, and academic historians started crediting her as a key figure behind the visualizations that proved seafloor spreading and plate tectonics existed. Marie Tharp's greatest gift wasn't simply technical, it was interpretive. She had an uncanny ability to recognize patterns in numerical data that others missed. She could see the unseen. This ability wasn't always valued. Her suggestion that the ocean floor was not flat, but instead filled with mountains and valleys, was considered laughable by many in the scientific community at that time. The prevailing belief, despite echo-sounding data, was that the seafloor was a featureless abyss. Tharp shattered that illusion. Her mapping of the mid-Atlantic ridge provided evidence for Harry Hess's seafloor spreading hypothesis, which proposed that new crust was created at oceanic ridges and pushed outward, forcing continents apart. This helped turn the tide for plate tectonics, a theory that by the late 1960s became the unifying framework for geology. And if you're interested in seeing the map, I'm going to post that on my website at mathsciencehistory.com, as well as the link to the David Rumsey map collection that shows the map that Tharp masterminded. And while you're there, please remember to click on that coffee button and make a donation to Math Science History, because every donation that you make helps to keep this free and educational website and podcast up and running. And I can't begin to tell you how much I appreciate those previous donations and everybody's generosity to the podcast. Thank you. Marie Tharp didn't receive major recognition for her work. This came much later and only in accompanying materials or retrospective accounts, not as a printed credit on the map itself. So her formal recognition began in 1997. The Library of Congress honored Marie Tharp as one of the 4 greatest cartographers of the 20th century and displayed the world ocean floor map in an exhibition that credited her work. The map was not reissued with her name on it, but her authorship was acknowledged in the exhibition materials. In the early 2000s, historians such as Holly Felt in her biography, Soundings, and others began documenting Tharp's pivotal role and correcting the historical record. Posthumous exhibitions and educational reprints were made. In recent years, modern reproductions of the map used in classrooms, science centers, and online repositories often include her name in the caption or metadata, but again, not as part of the original publication. In 2001, the American Geophysical Union featured her legacy in its History of Geophysics volume, and by the early 2000s, National Geographic began publicly acknowledging her vital role in visualizing plate tectonics. In 2004, the Marie Tharp Fellowship was created for women to work with researchers at the Earth Institute of Columbia University. That same year, she donated her original hand-drawn maps and notes to the library's permanent collection. And soon after, she was honored by the Woods Hole Oceanographic Institution as one of the greatest women pioneers in oceanography. Even after her passing in 2006, recognition continued. In 2015, she was honored with the Google Doodle that brought her story to millions of people around the world. In 2015, the Tharp Moon Crater was named in her honor by the International Astronomical Union. NASA celebrated her as a visionary in Earth science during Women's History Month in 2020. And in 2022, a 72-foot research schooner was named after her by the Ocean Research Project. Finally, on March 8, 2023, on International Women's Day, the United States Secretary of the Navy, Carlos del Toro, renamed a ship in Tharp's honor and is now the USNS Marie Tharp. It took decades for the scientific community to fully appreciate her brilliance, but today, Tharp is remembered not just as a cartographer, but as a scientific visionary who helped reshape our understanding of the planet itself. Stories like Marie Tharp's remind us that science has never been the sole domain of those given permission to speak. It has always depended on those with the vision to see. Tharp didn't just map the ocean floor. She mapped a future where determination and insight can override exclusion. Her experience is a testament to how many vital contributions have been dismissed, delayed, or erased, not just by gender bias, but by the persistent gatekeeping that affects women, people of color, transgender individuals, and anyone outside the traditional image of a scientist. Honoring Tharp's legacy isn't just about looking back. It's about making sure the next Marie Tharp doesn't have to wait decades to be believed, credited, or heard. Because when science reflects the full range of human experience, it moves not just faster, but truer. Marie Tharp's most famous map, the 1977 World Ocean Floor, is more than a scientific artifact. It's a manifesto of persistence, a reminder that patience, precision, and the belief in evidence can overturn the most entrenched dogmas. And you can still see that map today. Its blue ridges, the red trenches revealing a once hidden topography that changed how we view the earth beneath our feet. And behind it all, a woman left behind, banned from the boat, making the most of her discoveries, penciling out a map with passion and brilliance. Marie Tharp's exclusion from sea voyages, publications, and recognition was not unique. She was part of a long lineage of brilliant women whose work was minimized or erased. But her story also highlights the broader issue of scientific exclusion, one that extends beyond gender. Today, we must also confront the historic and ongoing exclusion of transgender scientists, LGBTQ+ individuals, and people of color from scientific spaces and recognition. Science thrives on diversity of thought, but only if diverse voices are welcome and heard. Tharp's perseverance reminds us that exclusion doesn't mean irrelevance. It doesn't, and I hope many of you out there hear this and remember that. Exclusion doesn't mean you are irrelevant. You are relevant. It means that the institutions are failing, not the scientists. And it underscores how much potential we squander when we marginalize voices at the edge of visibility. Tharp saw the earth differently, not because she had special access, but because she had the vision to believe in what the data told her. She listened, and then she drew. Today, as we build a more inclusive scientific world around the world, her story reminds us that brilliance is not limited by gender, identity, or background. It's limited only by who gets heard and who gets believed. So keep drawing maps, not just of the seafloor, but of a world where every voice in science matters. And until next time, carpe diem. Thank you for tuning in to Math Science History. If you enjoyed today's episode, please leave a quick rating and review. They really help the podcast. You can find our transcripts at mathsciencehistory.com. And while you're there, remember to click on that coffee button because every dollar you donate supports a portion of our production costs and keeps our educational website free. Again, thank you for tuning in. And until next time, carpe diem.